down. Oh, I have to get my cheat sheet for this one, just like every other one. Okay, so today I want to talk about that next level of discovery, which is we've talked about a brief history of looking at our star, looking at the planets in our solar system, and today, yes. Is that you today? Yes. Why don't, while I preamble, you come find yours, and then we can put it on there. And then I won't skip it like I do. And today's lesson, after Deanna shares her news with us, is going to be all about... Thank you. Is going to be all about how we learn about stars other than ours. Things, stairs. Are you ready? Do you need to switch users to get the thing? Like what? Do you need to sign in to find it?
I don't know. It's on.
Yours is? Okay, yeah. So switch, log out and switch users. Okay, so here's what we're gonna do. We will do that toward the end. Okay, so while you find it, you got this too. Okay. Okay. Yes, guys. I feel like I'm competing, and I'm getting a little annoyed. Be quiet. Thank you. Yes.
Why is the 4.6 have a...
Because I drew a line through it. There's no message there. I just slipped. Okay. So, and we're going to talk about how we know about stars other. Be quiet. No, don't say you're sorry. Don't respond to him. Just be quiet. All right. You're holding up class. We've got lots to do today, and instead we're listening to you. Be quiet. So we want to start off today talking about stars that are far away. And one of the first things we need to talk about is, if you remember, when we worked last week back there, we measured things in kilometers and we got crazy big numbers, right? I mean, we got a number with 27 zeros when we started talking about long distances, which is not convenient. So before we can get going with anything else today, I have to talk about how we measure distances in space. Inside our solar system, we use a unit called the astronomical unit. An astronomical unit. And I have to look up the number. I think it is 159 billion kilometers, but I often report it wrong. 149.6. Is it 149? Look at you. It is. All right, so an astronomical unit is 149 million if we measure it in kilometers, right? So 149 million kilometers, which would be 149 billion meters, which is a pretty random number to pick. But why do we pick that number? This is the distance from? The sun. Very good. From the sun to? Earth. From the sun to the Earth. The average distance. And if we look at it here, you can see that that is one astronomical unit. And we use the abbreviation AU. Speaking. You got it. On the way. Oh, not right now because I'm on the projector. Who's kidding who? That's never going in. All right. So if you look here, within our solar system, that is a very effective measurement of distance. Does that make sense? So that would make Earth 1 astronomical unit. Mercury, the closest planet, is 0.39. Venus, 0.72. Mars, 1.52. You could keep going to the outer solar system. So it's a very convenient way for measuring within our solar system. All right, but beyond that, even an astronomical unit is a very, very small unit when we start talking about between stars. Outside our solar system, we use what we call the light year. Now, this is a little weird because year is something we measure not distance with. What do we measure with years? Time. So what does it mean by light year? Yes, sir.
How far light travels.
Good. So light travels 300,000 kilometers every second, which is a long distance. Light goes 300,000 kilometers in one tick of the second hand of a clock. And that means that in an entire year, light will travel 9.46 times 10 to the 12 kilometers. So that would be 9 followed by 12 zeros, kilometers. Long distance. 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You don't have to write that, no. So that'd be 1,000, million, billion. So that is 9 quadrillion kilometers. Long distance. Far, 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 far away. And in fact, the nearest galaxy to ours is about 2 million light years away. The nearest star which is called Proxima Centauri, is about 4 light years away. That's the nearest star. So when we look at Proxima Centauri, which we'll talk about when we actually get into stargazing, you can actually see it. You know that you're looking at what it looked like about 4 years ago, because it takes about 4 years for the light to get here. So I just want to mention that because as we talk about the rest of this note, I'm going to be talking about light years. So it's important to know what it is. A light year is a measure of the distance it takes for light to get here. The nearest star we can see is about 4 light years away. And I should mention, actually, the furthest stars we can see are about 12 billion light years away. Crazy, right? It's a long distance away. I should say there's no reason to write out the word light years at this point. We just put LY. So the nearest star, it takes the light about 4 years to get to us. We're seeing it what it looked like 4 years ago. The furthest stars away, we're seeing what they looked like about 12 billion years ago. I think the current number is 12.4. I can almost speak. As the distance to the furthest star that we can see, the distance of the visible universe. Now, how the heck do we look at something 12 billion light years away. Light that took 12 billion years to get here, and know anything about that star. And what I want to talk about to start is this. When we take, say, a piece of metal, or say a piece of wood or whatever, if we take something and we heat it up till it gets really hot, what happens to it? It starts to glow. What color will it start to glow first? Red. And if it gets hotter, it'll get yellowy. If it gets even hotter, yeah, and in the middle there, white. Good. Does that make sense? We know this when we heat things up. Ma'am. Shh. This is my stressed out face. I don't know if you can see it. It's my sleep deprived face. So, with that in mind, keep in mind, what is a star? It's a big ball of gas that's just glowing hot in space, right? Well, we know from our own experience heating things up that how hot something is changes what color it is. Does that make sense? So when something is really, really, really hot, it appears to be kind of really richly blue. When something is cool but still glowing, and by the way, when I say cool, I mean by star standards, not by like reach out and touch it standards. But for a star, 1,000 Kelvin, which is about 1,100 degrees Celsius, would be quite cool. That's about the temperature of a candle flame, and that looks quite red. Does that make sense? We know this intuitively. When we light up the Bunsen burner, what color is the flame to begin with? Yeah, kind of reddy orange. And it'd be somewhere between about 2,000 and 3,000 degrees right in the heart of that flame. But when we give it a bit of oxygen and really get it going, what happens to that flame? Yeah. Now the Bunsen burner, only very, very small portions of it are actually that hot. Just the parts that are actually glowing. You won't get something to be that hot using it, but still the actual inner portion of that flame, the gas itself, is that temperature. Does that make sense? Now the problem with a Bunsen burner is there's lots of cool air around to cool that down very quickly, so you're still never going to get an object up to that temperature. Does that make sense? But in a star, you've got all that temperature, there's no cool air blowing across it, you're in the nothingness of space, and it's a huge nuclear reaction, right? A star is just a big ball of nuclear explosions getting hotter and hotter. And we can tell how hot a star is just by looking at it. And in fact, when we take when we photograph stars, we photograph them slightly out of focus. I mean, now we have computers that do this, but in the early days, we simply photograph stars slightly out of focus to see their color. Does anyone have like a nice camera at home and they've seen this effect, or maybe you've used a camera in class where if you put it out of focus, small lights all of a sudden turn into big spheres, the shape of the aperture? Seen that before? We do the same effect with this to see the color of a star. And then once we see the color, we can just compare it to this chart and we can know the temperature. So first of all, that's kind of cool. Something that is 12 billion light years away, something that was glowing 12 billion years ago, and the light's been traveling all this time to get to us. We can look at that light and we can describe the object as it was when it made that light. We can say how hot it was. Kind of cool, right? Oh, I think that's pretty amazing. Sorry? Oh, it wasn't even an intentional pun. Okay, all right, let's focus. So, we photograph stars slightly out of focus to see their color. Oh, also, don't let me forget, Mrs. Farmer, I don't know if she has you stressed out and scared yet, but she certainly has me stressed out and scared. So at 10:10, a couple people need to go. I believe just the two of you. Is that true? You're heading down. Don't let me forget. Is it 10:15? Then you got 10 minutes. All right. So just by looking at a star, we can see its range. So looking at actual stars here, we have from red to orange to yellow, right? And then up around here we see the white. And then here we get the blues. And I'm just going to kind of put them in there because they kind of range from light blue to dark blue. But we can see these stars, and we actually have real examples. The red stars are the coolest stars. That makes sense? And so Betelgeuse is an example. Betelgeuse, though it is where the name Betelgeuse comes from. Betelgeuse is the biggest star, or one of the biggest stars we know of, and it's a big red thing. It's red hot. Antares, Arcturus, and Aldebaran are orange in the sky. Our sun gives off yellow light, right? It's not a pure white. It's kind of yellowy. And so does Alpha Centauri, which is one of our nearest neighbors, the second closest star to us. We get up to like Polaris, which is the North Star. The North Star, very white light. It's hotter than our star. And then Vegas and Sirius, which you can see in the sky, are 7,500, 1,100. They're getting hotter. They look blue. Rigel and Spica, even bluer. Venus is extremely, it's a rich, rich, rich blue when you look at it through a telescope and put it a little out of focus. And so looking at these stars, we're able to know how hot they are. But what I want to note is this. The temperature of a star, and I'm going to say normal star. And when I say normal, I mean not a red giant, not a white dwarf. All right, a star in its main cycle. We call these main sequence stars. But we're talking about stars before they've become a red giant or before they become a white dwarf, just in the early stage. The temperature of a normal star depends on its mass. Why might that be? Why would the temperature of a star depend on its mass? Yes? Good thinking. That's exactly right. Think of it this way. What would you expect to be hot? An explosion where I use, a small little, like one of these little beakers full of gasoline shaken with air? Or an explosion where I take like a jerry can full of gasoline and shake it and make it. Which one's going to be hot? Jerry can, right? Does that make sense? Cool. So the temperature of a normal star depends on its size. And this is going to lead us to what we call the HR diagram, the Hertzsprung-Russell diagram. You do not need to remember the name. HR diagram is fine. But it's an important concept, which is, and I hope this printed okay for you. It did, good. This pathway here is all of the standard stars. And basically, it works like this. Here we have cool stars, low temperature. How do you know it's low temperature? Oh, sure, yeah. Sure? Because they're red. Good. Hi, what can I say?
Gifts.
Oh, thank you. From who? From Mr.
Ventnor.
Ventnor. Thank you. So over here we have cool, low temperature stars. If we look at this scale, how do we know that they are cool, relatively speaking? Color, right? Because they're orange and red. What then do we have over here? We have hot stars, right? High temp. Now, here's the interesting thing. What we've learned is that there's a relationship between the temperature of a star and over here, it uses the term absolute magnitude. We'll talk about that. But really, we're talking about brightness. Brightness. And as a rule of thumb, we can see that hotter stars are bright. And as a general rule, cool stars are dim. Good. So, and that's true for all of the main sequence stars. So, hot stars are bright. Cool stars are dim. Sorry, I can make that a little bigger. Yes. Yeah, of course. And this means that if we know the color of a star, knowing the color of a star actually tells us a few things. Thank you very much. Just looking through a telescope and looking at the color, well, we've already said it tells us the temperature of that star. But it doesn't just tell us the temperature, because if we know the temperature, we also know how bright the star should be. So if we know the color of a star, we should know its temperature, and we should know how bright it is. And we can just look it up on this HR diagram. You can see it's not a perfect straight line, right? Yes, you do. Go ahead, guys. I mean, we could spend a lot of time talking about how they made this diagram, how we figured all this information out. I don't, unfortunately, have time to devote to that. It's really interesting. It's worth a read. Basically, we were able to figure this out with stars that are really close. And once we knew it was true for all stars, we can then apply it to stars that are far away, that were harder to look at. All right. All of which is to say this. The last stage in the game is to know this. And I put a little diagram that I stole here. Here on Earth, I want you to tell me about star A and star B in this picture as they actually are. What do we know about star A and star B? Yeah. A is dim and B is bright. Good. So A is dim, B is bright. Hey, right there, what could you tell me about these stars? What must be true about A? Good. So A is dim. It's cool. What would its color? Yeah, you can write this. What would its color be like? Yeah, it's probably red or orange. And what could you tell me about B? Yeah, so it's dim, bright, it's big. I'll actually put that. This would be on the small side. And this one here is bright, It's big. What else can you tell me about? Yeah. Yeah, it's probably a hot star, as long as they're both main sequence stars. What do we think back there? What else can you tell me about star B?
Blue or white.
Very good. So it'd probably be white or maybe blue. Okay. Does that make sense? Now here's something interesting. On Earth, from where we are, which one is closer to us? A. A is closer and B is further. Now, in real space, regardless of anything else, which star is actually brighter? B. But to us, to the observer here on Earth, what are we going to see? Yeah, we might see A as brighter or... Good. And in this particular example, the textbook I stole this from shamelessly has picked two stars where to us they appear to be the same brightness. Does that make sense? Why does A, which we know is dimmer, look to us like it's as bright as B? Why does it look as bright? Good. You can try this yourself. If you have a flashlight and you come right up to my eyes and you think, you know what, Orlando, you're in a bad mood today. I'm going to shine this flashlight in your eyes. Right from up close. I'll say, you're right, I am in a bad mood today. Sorry about that. And then you shine the flashlight in my eyes and I'll be like, ah, right, it's going to hurt. On the other hand, if you're like, you know what, Orlando, you're in a bad mood today and I don't want to be anywhere near you, and you go to the other end of the room and you shine the flashlight in my eyes, what am I going to find? Probably not as bad. I might still go like, ah. What if you went to the other side of the hallway and shone it at me?
You wouldn't see it.
I'm not going to notice it, right? It might look like a little light. So the further you are from a light source, the less bright it appears. Yes. Yeah, of course. So, brightness decreases over distance. And so the absolute magnitude, and I'm just going to put mag, is how bright a star actually is. Can I fit it? Oh, I kind of can. I had to cheat. Sorry. So the absolute magnitude is how bright that star really is out in space. And what do we call the apparent magnitude? What's that mean? What do you think? If the absolute magnitude is how bright a star actually is shining out in space, the apparent magnitude is? 2. Yeah, to be to us here on Earth. Good. How bright the star is in the sky. But remember, just by the color of a star, we can tell how bright it really is, right? So if we see a really blue star out into space, and we know it's a main sequence star, we know it's got to be really, really bright. So if it looks really dim to us, what must be true? What do you think? It's got to be far away. If we see a red, red, red star, like Betelgeuse in the sky. Betelgeuse is one of the big stars in our sky. Betelgeuse, Betelgeuse, Betelgeuse. Yes. Yep. Betelgeuse is red, which means it's a relatively cool star, which means it's bright or dim? Dim. But it looks really bright to us. What must be true about it then? It's got to be close. Does that make sense? So, since we know how bright stars actually are, I'm just going to put in brackets the color Their appearance tells us how far away they are. Appearance. Any good spellers out there? Appearance. Help me out.
R-A-N.
E-N-C-E? So that was right. Why does that look so weird to me? Well, don't think even you. You're probably good at spelling, and I...
Nope, it's an A.
It's an A. Now that looks even more wrong to me.
Whatever, the English language is just scribbling on paper anyway.
Well, that's not true.
And scribbling we can understand.
I don't like it.
Oh, no, I believe you. I was responding to her. That makes me uncomfortable, but okay. I wish I'd never used this word. Now I've got to memorize this. Okay. So tomorrow you're going to have a little activity where we actually look at some real photographs of real stars, and we compare their brightness to their color, and we rate them from far to close by. We're going to actually use the HR diagram. Does that make sense? Now, I want to mention one more thing. We have to watch out because we said that this holds true for all of the main sequence stars, right? All the stars that are in the regular life cycle. What are the other two ways we see stars? Right when a star is nearing to use up all of its hydrogen, what stage of its star life does it enter? What does it become? Yes, sir. Yeah, what kind of giant? Yeah, a supergiant or a regular giant. What color are they? Red. So every star towards the end of its life cycle, no matter what, gets really big and really red, which actually means, is that really hot? It's actually really cool. Right? So keep in mind, normally big stars are really hot stars, right? Normally the bigger, the whiter, the hotter. But the red giants are the exception. So towards the end of their life, they become red giants, which are weird. And then after that, they become, when it uses up all of its hydrogen, what's it become? A black hole, a neutron star, or a white dwarf. And neutron stars and black holes don't even show up on this diagram because they're so bizarre. But white dwarfs, again, usually small stars are really the relatively cool ones, right? They're red hot. White dwarfs are really small stars that are white hot. So if you go back and look at the HR diagram, all of the normal stars fall on this plane. And then we have some things that are messed up. The white dwarfs are much hotter than you'd expect them to be for their size. And the red giants are much colder than you'd expect them to be for their size. Does that make sense? I hope. Yeah, and then the supergiants are these guys here who will eventually become black holes. But if it's a main sequence star, we can work it out. So, man, I'm going to actually finish a note on time. You guys should, like, go home and be like, "Dear diary, Orlando finished a note in less than 74 minutes and 12 seconds today." And then you should, like, get your parents to buy a lottery ticket. Yeah, I don't know. This is not my usual way of doing things. So, all of which is to say this. Again, you're going to do an actual activity based on this tomorrow. When we actually chart a star, the first thing we do, is we take this kind of out of focus picture, right? And we look at the color of the star. So the first thing we do is we observe the star's color. From that, what do we know? When we look at a star's color, what do we know? Yep. So now we know its temperature, right? What else do we know? Good. We know its size. Because again, which stars are big stars if they're in the main sequence? Those are the red giants and things like that. But on the main sequence, in a main star, a typical star, which ones are really hot? Remember we said it's like which one's going to burn hot, the little flask of gasoline or the big jerry can? The big jerry can. So the bigger the star for a normal star, the hotter it is, right? And maybe we should even put that here. Hot equals big. Cool equals small. But we don't just know that. We know its temperature, we know its size, and then we can look at the HR diagram and we can learn one more thing about it. Because we know that hot stars burn bright and cool stars burn dim. So we can figure out just by looking at its color how hot it is, how big it is, and how bright it is. Now, using its brightness, what can I then figure out about this star? So if I see this star and it's white, 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 white hot, and I know it's a main sequence star, we'll talk another day about how we know that exactly, but I see this white hot main sequence star that's really dim in the sky, what do I know? What do I know? That's farther away, because I know the star is really quite bright, so if it looks dim in the sky, it's got to be far away. Now, if I see a white, white, white star in the sky and it's super bright, I know it is close. Good. So from that, we can figure out the distance. And we do that by comparing actual brightness to expected. And so every time we discover a new star, this is the process we go through. We look at that star, and that's why you'll read on the news, sometimes it's like, we found a new star in such and such a galaxy, and it's like the same temperature as ours. How do they know that? This is how they know that. It's actually really easy. They just look at what color it is. It's a yellow sun like ours, same temperature as ours. Yes, sir. What did I put? Comparing actual brightness to expected?
Yes, that's right.
I think that's actually okay,
Yeah.
which I'd like to point out is a rare case of me not screwing the grammar up. It's okay. I usually am, so it's usually a safe assumption that I'm wrong. But you know what they say, even a broken clock's right twice a day. So, assuming like you measure in 12 hours, I have family who live in Britain, and their clocks just go up to 24. Right, if they have a clock like this on the wall, like at noon it would say 12, and then when ours would say 1 in the afternoon, theirs just says 13, and when ours would say 8, theirs just says 20, and just keeps counting up to 24. So in Britain, a broken clock's only right once a day. So there you go. Okay, so a couple more things to do today, and then I'll give you the duration of the time. I'm going to go grab the Chromebooks. Actually, would you mind going to grab the Chromebooks? And you can kind of keep plugging away on your research project. I wish I had a computer lab for us. They were all stolen. Rice, they were stolen, but that's okay. But first, I'm going to ask Deanna to come up and do her science in the news. Is it a video?
Yeah.
Wunderschön. All right. Okay, so Deanna, where did you find this?
I don't remember.